Hello, my name is Zachary Epp, and I will be presenting Lie groups and the formation of the standard model of particle physics. First off, what is the standard model? The standard model is basically the foundation of all particle physics. It is the most impressive thing we've come up with. It basically describes the discrete particles that make up our reality, as well as the fundamental forces that govern that reality. To start, we gotta understand notation. Einstein notation. Basically, the whole gimmick is incredibly annoying and confusing, and you just drop the sigma. Our particle needs to exist, so that means it needs to exist in three-dimensional space. That means it has an x, a y component, and a z component, and it also progresses in time. Now, time isn't exactly the same as everything else, so we need to account for that, and then we account for that by accounting the covariant vector. And basically, the whole thing with that gimmick is that we just apply a negative on the thing, but our time is a little bit negative, so we just multiply those two together, and it works out. We also apply the same thing with the derivative. It's the whole gimmick is that you just remove the sigma. It's that simple. Now we need our Lagrangian. Our Lagrangian is how we actually apply the groups and apply the symmetries to our system. It's how we actually understand what the particle is and what we're working with. The basic idea is that you have the kinetic energy and the potential energy. That's the system of equations. We're just applying every single aspect we know that should exist about a particle, and we can apply our group structure to see which ones stick and which ones don't. Now, our basic idea doesn't just apply the basic energies of the system. We also need to actually have the space version into it. So our Lagrangian is basically just the spatially dependent version of the basic Lagrangian. So, well, how do we actually apply the group and find our interesting parts of our Lagrangian? Well, basically, I got a four-step process. First, we build a Lagrangian with our bunch of numbers and stuff. Don't worry about that for now. Secondly, we find the group that should be invariant. We find a property that exists that we can apply the group onto our vector, and it does nothing. And then we can modify the Lagrangian to maintain that symmetry. And then 4, we can determine the implications of that. If we construct our Lagrangian in such a way that certain constants mean certain things, if some constants aren't maintained with the symmetry and they're all 0, then that means that those properties don't exist. So let's actually build our Lagrangian. Don't worry too much about what's inside of these things here. Just notice the constants that we can change on either front of these terms. What we really want to talk about is these constants. Now, why did we add these terms? This is our mass term. Einstein tells us that mass is just another form of energy. That's what we're guessing. Secondly, if our particle is moving, that's also another form of kinetic energy. How it's moving? Well, it can either rotate or move in a line, move kinetically. That's either energy with rotational velocity or motion. This fourth term, you don't need to worry about too much because it doesn't. This fourth term, you don't need to actually worry about too much. It's kind of like how much energy is going in and out of the system. That'll have consequences later. It's a little bit confusing. Our second task is to find a group that should be invariant. Now, quantum mechanics has a way of describing probability to us. Basically, if we have a wave function and we multiply it by a complex conjugate, it starts to describe probability. If we integrate that probability over all space, well, our particle is definitely somewhere, so it equals unity. Turns out, if we apply U1 onto this wave function, then you get unity. So our group, U1, doesn't actually do anything to our system. This is our group. So let's modify the Lagrangian to maintain this symmetry. First off, normal derivatives cause a problem, and there's a slight bit of nuance about what the derivative is actually doing. If we apply our U1 to our phi, it needs to be invariant in that it doesn't matter if it's inside or outside the derivative. The problem with that is that it does actually matter. E to the I AU, that AU is there because our particle actually has like a position in space. It can't just be regular theta. This is still a single number though. This is not a vector. This is just a variable. But notice how this, if you expand it out e to the I theta for an arbitrary AU, that doesn't just equal U1 derivative phi. It actually starts to has this ugly term that we don't want in there. So we use the difference to construct how the field should act with a new derivative operator called the contravariant derivative. Basically, this is what we're going to actually sticking into our Lagrangian. Now, this doesn't work. This is just like U1 multiplied with the old thing we had. This is a little bit too simple. So we need to actually make sure it works with the derivatives. Now, we defined an old derivative earlier, and we need to apply the same rules on this new derivative. If we apply this with this, and we sort of do a little bit of math, we find that this also equals to all of this, and it has just like the regular vector term that we had before, but with another little derivative slapped onto it with that arbitrary function that we defined before. Our fourth task is to determine the implications. We replace the arbitrary vectors with the one that satisfies U1 invariance. So we turn all of our regular A mu and A superscript mu into our C sub mu that we had from before. And basically we just expand this out in the whole equation. Our first term, is this energy invariant? if it looks exactly the same, if we applied our transformation to it and it looks exactly the same, then it's fine. Then it exists. But if it has this remaining term, and if there's no way we can modify this constant for it to cancel out, then it can't exist. Then C1 must be equal to 0, because we know that we define that transformation on this term, it must be equal to this term still. Our full Lagrangian still needs to have nothing to do with U1. Now our second term, this is the first kinetic energy term. Is this energy invariant? We have the same issue now. We need to make sure that is C2, can we modify it in some way with C1 to make these terms cancel out? But unfortunately, everything past C2 here, that's all arbitrary nonsense. So we can't actually cancel this out directly in any way. These don't actually look that similar, despite them looking both like gobbledygook. Unfortunately, these aren't really related. So maybe we'll have better luck in the third term. Our third term does actually look exactly like the remainder. The remainder for the third term actually looks exactly like the motion term we had in C2. This is exactly the same. So sure enough, if we define C2 equal to negative C3, then these terms can cancel out, and we're just left with our invariant terms that don't change under U1. Okay, so we're on the right process here. What's the fourth term? The fourth term is our weird sort of divergence energy term, depending on like how much energy is entering and exiting the system. Now, unfortunately, this term looks nothing like our other three terms, so we can't actually make this remainder term look anything like the one we had for the third, second, and first term. So, unfortunately, we're actually forced to call C4 equal to C1 equals 0, because remember, we never resolved that first mass term, so that must also equal to 0. But wait, that's actually a good thing. We just discovered that our particle doesn't have the energy associated with mass, so it's massless. So it doesn't have mass. What particle doesn't have mass? It's also not the no divergence term is a little bit nuanced, but that also sort of implies that it's not a longitudinal wave. It doesn't. The energy that it's like exiting and entering its system doesn't travel along its path. What system doesn't have mass? Well, if you define this ugly notation with double indices, now we love our indices, at least someone does, and we define C2 equals negative 1/2. There is actually a way of formulating that. I don't know how. But you can actually convert that final Lagrangian that we had with our C4 equals C1 equals 0, and then it looks like the Lagrangian for electromagnetism. So we just basically discovered the photon using U1. U1 just gave us the fundamental particle that described electromagnetism, and I don't even have a particle accelerator, and I just discovered that the photon must be massless because we added a mass term to it. We know that the photon must be invariant under U1 by that quantum mechanical theory that we had. But the Lagrangian said no. The Lagrangian said that this photon doesn't have a mass term to it, that C1 must be equal to 0. And we can apply this for other groups as well. Unfortunately, it gets a lot more complicated. And we can have different combinations of our group with the cross there to describe our entire standard model. Our entire standard model is just different combinations of the same three groups. And they're all like spherical, nice looking groups. Now, do they act nice? No, they're really confusing. This one, SU2 that I'm going to be working with, that's a matrix. Now, U1 was really convenient because it had just like one constant that always applied to anything. But this acts as a matrices, which means it needs to act on a vector. It can't act on a single constant. Basically, what that means is that we apply the Pauli matrices that we actually saw in class today onto our tensor, and everything is tensors now. I'm not going to bore you with the details, but basically the contravariant derivative that we described before for U1, it looks like this with some constant g and the tensor W sub u. Basically, it has implications that every particle has a pair, so each up has its down, each term has its strange, each top has its bottom, and we also have each particle must have its anti-particle. So if we have one particle that's like an up quark, we must also have an anti-up quark, and they must annihilate and make all the energy happy. In conclusion, we found that U1 is the group that describes the photon. We found that the photon is not a longitudinal wave. We found that it also doesn't have mass. And we also found that it actually spins. If you can imagine what a wave function spinning looks like. I hope you're interested enough to try the standard model for yourself, because we could really use some better notation.